Okay, so writing all of those electron configurations, especially for ones like rubidium and argon and stuff like that, can get a little bit taxing because there's a lot of electrons to show in an orbital diagram and an electron configuration. So the electron configurations of all elements, except for hydrogen and helium, can be represented using a noble gas core. Okay, so what I want to do to illustrate this is to write the electron configuration for both potassium and argon, which we just did. So we did argon as 1s2, 2s2, 2p6, 3s2, 3p6, so that's our 18 electrons. So let's try potassium. Well, potassium has 19 electrons, so it's going to start off very similar to argon. 1s2, 2s2, 2p6, 3s2, 3p6, so that's 18 electrons. We now have 1 electron to give away, so that's going to go in the 4s if we follow our diagram, and that 1 electron is going to go there. So if we compare our answers, everything up through 3p6 is the exact same between argon and potassium because they have 18 electrons in common. Okay, so they have 18 electrons in common. What the noble gas core is saying is, well, argon is a noble gas, so we could say that this section is really close to argon, right? It's the exact same as argon. It only differs from argon by what comes after those 18 electrons. So the noble gas core is a way of simplifying our electron configuration for all of our elements so that we don't have to show every single electron, because the noble gases have electrons in common with all of our elements. So the electron configurations are shown here. So this is exactly what we just showed. So because the electron configuration going up through 3p6 is the same, we can simplify our potassium expression to say, well, the first few, oops, I thought that was a highlighter. The first portion here is made up of electrons that are from argon. The only difference is here, so we can simplify by saying, well, we're going to put argon in brackets, and everything that's different from argon comes after those brackets. So whatever closest noble gas to our element on the periodic table is going to be our noble gas core. That's the maximum number of electrons that our element has in common with that noble gas. Okay, so if you look on your periodic table, the noble gas that comes before potassium is argon. So I should say comes before our element. Okay, so let's do some practice problems here. So we want to write the electron configuration for arsenic, which has 33 electrons in its ground state, meaning that they're all going to be, we're just going to follow these. When it says in the ground state, just it means nothing, okay? We can basically ignore that because we're not moving any of those electrons into a higher lying excited state or any of those higher states. So that's just what it's saying. So the setup for this problem, well, if we look at where arsenic is on our periodic table, the noble gas that comes before it is argon. So of the 33 electrons that arsenic has, 18 of those electrons are similar to arsenic or argon. So our noble gas core is going to be Ar. Okay, so then we're going to find 15 electrons that differ between argon and arsenic. So we then follow our diagram for those 15 electrons. And we're not starting here because argon ended at 3p. So we've already done this portion of our diagram. So our next portion that we have to do for our 15 electrons is now starting with 4s, which has 2. Then we jump into the 3d, which has 10, so that's 12 of our electrons left. And then we finally go to 4p. So we've used 12, we have 3 electrons left for arsenic. So that is our noble gas configuration of arsenic using argon as our noble gas. What we can't do is say, well, krypton is really close to it. It's not like we can say Kr minus 3 electrons. We can't do that. So it has to be the noble gas that comes before it. It's before arsenic. Okay, so let's continue to practice that with electrons coming before the noble gas that comes before it. So if we're looking at sulfur, we want to do the noble gas core configuration for sulfur. Well, sulfur is right here. So the noble gas that comes before it, well, I'm going to work backwards from my periodic table, okay, which leads me to neon. So we have neon, okay, neon has 10 electrons, sulfur has 16 electrons, so we have 6 electrons that we have to fill in. If we look at our chart, neon ends in the 2p, so our next stop on our plot, on our diagram, is the 3s, right? 3s comes after 2p, so we have 3s2, and then we have 3p, which comes next. We have 1, 2, 3, 4 electrons of sulfur left over. Okay, now what you could do, if this is confusing for you, is you can write out the full electron configuration for sulfur and then cut off where those 10 electrons come from neon. So you could write it as 1s2, 2s2, 2p6, 3s2, 3p4. You could then say, okay, I know neon has 10 electrons, so that's 2, 4, 10. So that's 10 electrons. So you write those as neon, and then 3s2, 3p4. Okay, however way you want to write it. Writing it out this way, the extended way, is kind of not the purpose of the noble gas core because it's meant to simplify. So you don't have to write all of those out, but as you're learning this and as you're getting the hang of this and starting to see the trends and kind of what happens over and over, the periodicity of it all, hopefully that'll then start to show you how to do it without having to draw out the entire electron configuration. Okay, so let's try another one. Let's do antimony. Antimony has one of those funny element symbols. Antimony is Sb. Sb is down here. Okay, so the noble gas, the noble gas that comes before antimony, we're going to work backwards. We're going to go up to 4, is krypton. Kr. Krypton has how many electrons? 36 electrons. Antimony has 51 electrons, so we need to get up to 15 extra electrons after Kr. Okay, so krypton ends in the 4p orbital. Again, if you wanted to write out the full electron configuration for antimony and then cut off at the 36th electron and show that as krypton, you're more than welcome to do that. So krypton then comes after that is 5s2. If we then follow our diagram, 4d10 comes after 5s2. And then after 4d10 we have 5p, but I don't have enough electrons. There's only 3 electrons left, so they will go in my p orbital. Okay. If it feels like I'm going a little too fast, feel free to pause the video, write out the full electron configurations for each of these elements, find the overlapping electrons with the noble gases, cut those out, and put them in as in their little brackets so that it's easy for you to see it. Okay, so just like we did for sulfur. Okay, let's try one more. So we have iron. Iron is Fe. Fe is right here on our periodic table. So if we work backwards, we're going to have a noble gas core of argon again, Ar, which has 18 electrons, and iron has 26, so we need another 8 electrons to add on to it. So we know that argon ends at 3p, so we're going to go, next is our 4s, which has 2. Again, we're following our diagram. So next up after 3p is 4s, and after 4s is our 3d. Now I only had 8 electrons, I've already used 2, so my last 6 electrons are going to be in the 3d orbital for iron. Okay, so again, we can write this out as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, and we can say, okay, argon has 18 electrons. That's 18 electrons right there. So these are argon. We ignore those and say everything else that comes after it is for iron. 4s2, 3d6. Okay. Before we move on, I just want to reiterate that these electron configurations, they do just take practice, following the diagram, following our rules, writing out your orbital diagrams, using those to write your electron configurations. Those are all how we learn. Okay, so doing those step by step will help you learn to hopefully get to the point where you know the order 1s2, 2s2, 2p6, 3s2, so on and so on. You'll start getting into your head, okay, that you won't even need the orbital diagram to then write the configuration. Then, after you know the configuration, you won't even need to write the whole one out to write the noble gas configuration. Okay, so just keep practicing them. If you need more practice, just pull out your periodic table and just pick a random element and write out its electron configuration. That's always useful. And also, start working on your ALEX homework, because they have a lot of practice in there for you as well. And you can always redo problems with no effect to your grade. Okay, you can always use your unlimited attempts to get more and more practice. It's all about practice. Okay, so the electrons that are occupying the outermost shell or the outermost orbitals are called valence electrons. Valence electrons are the ones in our outermost orbitals. Those electrons are found in the orbitals with the highest n value. Okay, so we typically show this. They're going to be the ones that come after that noble gas core in our noble gas configuration. So here I have one for sodium. Sodium has 11 electrons, so 1s2, 2s2, 2p6, 3s1. Its noble gas core is neon, so neon 3s1. Sodium then has 1 valence electron because the highest n is 3. That's our highest n value. That's like our outermost shell. So here's our nucleus again. There's n equals 1, n equals 2, n equals 3. So in sodium, we have electrons here, and then we have 1 electron out there. There's only 1 electron in our outermost shell, so that is our valence electron. It is the electron in the n shell that is of the highest number. So n, in this case, was 3. That's our highest n. There's 1 electron, so there's 1 valence electron. The non-valence electrons, the electrons that are not in that highest n value, those are called our core electrons and are electrons that match the noble gas. Okay, so our core electrons in sodium are 1s2, 2s2, 2p6, so that's 10 core electrons. Neon also has 10 electrons. Okay, so anything that comes after the noble gas would be considered valence. There's one stipulation to that we'll talk about here in a second. So anything that comes after that noble gas is our valence electron. Our core electrons are then the ones that match that noble gas. We can group the elements according to the type of subshell that their valence electrons exist in. And we refer to these as blocks on the periodic table. So if you look through all of our previous electron configurations that we've written so far, you've noticed that where we've ended kind of is in different types of orbitals depending on where we're at on the periodic table. Maybe we left off with unpaired electrons in the S or the P or the D. Okay, so that's what we're referring to as being able to group them based on where their valence electrons are. So we have the S block. I'm going to try to highlight these. So the S block is right here. So that's for groups 1 and 2. Okay, their valence electrons are in the s orbital. So if you look at what we did for sodium, we did lithium, we did magnesium and potassium. Okay, we ended up with our last electrons being in the s orbitals. We then have the p block, okay, which is over here, the other side of our periodic table, and this is for groups 3A through 8A, or 13 through 18. Okay, their valence electrons end up in a p orbital. Next, we have our D block. Okay, this is our transition metals. Okay, so we'll write this as our transition metals. So what we just did with iron, its last electrons, those unpaired electrons, those last electrons that we had, they ended up in the d orbital. So that's our D block. Transition metals have their valence electrons in the d orbitals. And finally, we have the F block, where their valence electrons are in the f orbitals. So that's our lanthanides and our actinides, if you remember our grouping names from our previous lessons. Okay, so it's also really useful as you're going through and utilizing your own periodic table and writing these electron configurations, because if you have an atom that's in the p block, you know that its valence electrons, its last electrons, should be in a p orbital, and if they're not, well, then you did something wrong and you should redo it. Okay, so it's a good way to kind of help yourself orient yourself on the periodic table as to where those last electrons should be. Also, because we have, if you look at our periodic table here, it's labeled 1s, 2s, 2p. This version of the periodic table follows that list, that diagram that we have to follow, because you can start reading the periodic table and its electron configurations from left to right. So you have 1s. Once you're done with 1s, you jump down and you do 2s. After 2s, you have 2p. Once you're done with 2p, you do 3s, which is just like our diagram. Then we have 3p. And then we have 4s. And then that's where we jump into the 3d, like our weird rule says, that we go 3d, and then 4p, and so on and so forth. So if you start reading the periodic table from left to right, you don't even need that diagram anymore, because the periodic table tells you the order that the electron configuration should be in, as long as you remember that at the transition metals, okay, your values start to change with your d orbitals. They go down by 1. Okay, so again, you're more than welcome to use that orbital diagram, or that diagram that I gave you previously, that is available to you on all of your tests, so you can always use that, but your periodic table is equally as useful. Okay, so to go along with that, there is a distinct pattern to the electron configurations of the elements in a particular group, because they all have the same number of valence electrons. So all of the elements in group 1 have 1 valence electron, and we can see that by their electron configurations. Yes, they vary in their noble gas, but their last electrons, their valence electrons, are all in the s, and they all have 1. So group 1, group 1a, has 1 valence electron. Then when we get to group 2, or group 2a, they have 2 valence electrons, which we can see by having 2s2, 3s2, 4s2, everything like that. They all have the same number of valence electrons, 2. So our group numbers tell us how many valence electrons we have. So all elements that are in the p block are going to have their valence electrons in both s and p orbitals. Okay, so if we look at phosphorus, its valence electrons are in 3s2 and 3p3. Okay, so it has a total of 5 valence electrons. Okay, now D block elements, or our transition metals, are a little bit trickier, okay, because that's where we start to see the difference in our N values. So all the D block metals, or D block elements, the transition metals, have their valence electrons in both being the important word there, the s and the d orbitals. So if we look at vanadium, we have argon 4s2 3d3, okay, its valence electrons are in the 4s and the 3d. So it also has a total of 5 valence electrons. Okay, now this is an exception, so we're going to point this up there. This is an exception to that highest N rule because your N of 3 and your N of 4 shells are not totally filled with electrons yet, so they are all considered valence electrons in both the 4s and the 3d. And then, you know, further on it could be the 5s and the 4d and everything like that. So for our D block elements, they exist in both the s and the d orbitals. Okay, so again, we can use our group numbers like we did for group 1 and 2 to tell us how many valence electrons we have. So for our S and our D blocks, our group number is equal to our valence electrons. So group 1 has 1 valence electron, group 2 has 2 valence electrons, group 3 has 3 valence, or 3b has 3, 4, 5, there's vanadium, which we just said has 5, and so on and so forth. Okay, all of our group numbers that we have here tell us our number of valence electrons. So if I said, what is, I don't know, palladium, PD, palladium, how many valence electrons does it have? Well, it's in group 10, so it has 10 valence electrons. For the P block elements, there's 2 ways to tell how many valence electrons it has, and it depends on which notation you're looking at on your periodic table. So if you're looking at the teens, so 13, 14, 15, 16, 17, and 18, take that number and subtract out 10, and that tells you how many valence electrons it has. So oxygen is in group 16. 16 minus 10 is 6 valence electrons. Okay, you have to do the subtraction by 10 because if you look at oxygen, it has 6 valence electrons. It doesn't have 16, can have 16 valence electrons because there's only 8 electrons for it to have. Okay, so oxygen has 6 valence electrons. Another way you can look at it is if you look at the A notation, 3A, 4A, 5A, 6A, 7A, and 8A. If you just look at that group number with the A on it, tells you how many valence electrons it is because they differ just by 10. So boron has 3 valence, nitrogen has 5 valence. Okay, so you can look at it either way. So I have the example here of selenium. Selenium is number 34. It's right here. How many valence electrons does it have? Well, it's in group 16, so I would do 16 minus 10, 6 valence. Or I can look and see that it's in group 6A. That's 6 valence electrons. Okay, so you can look at it either way. Let's see. Okay, so we did, these were the 3 examples we did before with our noble gas configurations. Let's figure out how many valence electrons each of these have. And feel free to look at your own periodic table and look at the group numbers to show that it corresponds to the same thing. So sulfur, that's a p block element. We see it in the p block. So its valence electrons are in both the s and the p orbitals. So we could just add up the electrons from s and p. That's 6 valence electrons. It's also in group 16. So we do 16 minus 10, 6 valence, It's also in group 6A. Oops. So that's 6 valence. There's many ways to tell this, okay? So if you can't remember one way, try to remember the other. Let's see, so then we have antimony. Antimony is number 51. It's a p block element, so its valence electrons are only in the s and the p orbitals. So we ignore that d. Goodbye. That's the whole reason we have to subtract by 10 anyways. It's because of those 10 d orbitals, d electrons, okay? So it's only in the s and the p, so we add those up, and that's 5 valence electrons in antimony. Antimony is in group 15. We subtract off those 10 electrons, and we get 5 valence. It's also in group 5A, so that's 5 valence. Finally, we have iron. Iron is a d block element, so it's a transition metal, and transition metals have their valence electrons in the s and the d orbitals. So we look at s and d, we add those up, and we get 8 valence electrons. It's also in group 8, or 8b, so that would be 8 valence electrons. Okay, there are a couple exceptions, because what's chemistry without a few exceptions? If we haven't learned that from the beginning of the semester, well, we got to start learning it now, okay? Everything has an exception. There are a few exceptions to our electron configurations, specifically in chromium and in copper. Now, chromium has, 24 electrons, and its electron configuration is represented as argon 4s1 3d5. So if we look at that, so we have 4s1 3d5. Okay. Now this is different than what our typical rules of electron configurations would be, where we have 4s2 3d4. Okay, so the blue is the way that the accepted orbital diagram and configuration, and the red is the not expected one. And this is because of two things. First, because of Hund's rule, because what's happening, I'm going to zoom in here, is we want to maximize spin. Okay, so we have this one electron, we have 5 electrons of upspin and 1 electron of downspin. So what's going to happen is chromium says, well, I could maximize my spin by moving it up here and getting rid of that. That way, which is up here, I have 6 electrons all with upspin and no electrons with downspin. Okay, so we're first maximizing spin. The other reason is because orbitals like to be half filled or completely filled, if that's possible. Now, it's not like all of the electrons are going to rearrange so that there's completely filled orbitals and half filled orbitals or anything like that. This only happens with only a certain number of elements on the periodic table, specifically chromium and copper. Okay, so what's happening here is the S, so I'm going to look at my accepted one. The S only has 2 options. It's either filled with 2 or half filled with 1. So it's a 50-50. It's either one or the other, half filled or whole filled. Prior to me moving this electron, oops, that was a bad idea. Prior to me moving this electron, okay, never moved that, goodbye. The d orbital was 1 electron away from being half filled. So basically what's happening is the S is saying, well, I'm fine with being half filled with 1 electron if it means you can be half filled and I give you that 1 electron to be half filled. So it's just a more energetically favorable position for the element to be in to have 2 half-filled shells instead of 1 whole-filled shell and 1 almost half-filled shell. It's just more energetically favorable that way. Okay, so this happens for chromium. So this was our example for chromium. It also happens for copper for the same way. So here's the diagram for copper. The electron, this electron here, was originally down here in the 4s, but copper was 1 electron away from being a whole-filled D shell, so S is like, well, I'll be half-filled if it means you can be whole-filled. It's fine doing that. It's equally as energetically favorable. So it's just a rearrangement of these electrons so that these orbitals can be in a more energetically favored state. Now I want to point out that this only happens between the S and D orbitals in chromium, copper, molybdenum, and silver. Oops. Molybdenum MO and silver AG. It does not happen anywhere else on the periodic table. Very important. It's not like an s orbital or an s electron is going to move up to a p orbital. They're too far apart in energy. This only happens because, if you remember, when we started to mix those energy levels between s and d, okay, when we went from 4s to 3d, they're very close in energy. So those energy levels are close enough but they can exchange these electrons to be more energetically favorable. It only happens between the s and the d. It does not happen anywhere else. No other electrons will do this. No other orbitals will do this. Just s and d orbitals, and only for specifically chromium, copper, molybdenum, and silver. That is it. Nowhere else. So you just have to remember those 4. It's not happening anywhere else. Okay. So let's practice. Let's look at some of these electron configurations and let's determine the symbol for the element. These are all ground state configurations, meaning we can just ignore the fact that it says ground state because it's just going to tell us where all those electrons are. There's no extra energy or anything like that. So our first one is argon, 4s2, 3d10, 4p1. Now there's many ways you can go about figuring this out. You can look at the valence shells, like valence electrons. You can count up the total number of electrons. You can go from the noble gas and count however many electrons there are after that. You can do it many different ways. So you can start off by saying, well, argon has 18 electrons. So 18 plus 12 is 30, and then plus 1 more is 31 electrons. So 31 electrons is gallium. Okay. You can also say, well, its last electron is in a p orbital, so we know it's in the p shell, or p block, I should say. It's in the p block. And because p block elements have their valence electrons in the s and p, it has 3 valence electrons. 3 valence electrons. Okay, and because that last electron comes in the 4 shell, we're going to be in row 4. So row 4, group 3, because there's 3 valence electrons, is then gallium. You could do that as well. Or you could start with argon, and you know that there's, 13 electrons after that, so you go argon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You could do it many different ways. Okay, so let's see. Let me erase all of this. Get rid of that. So we can do our next one. What's our next one? Oh, come on. Why are we doing this? Erase. Goodbye. Okay, there we go. So we have krypton, 5s2, 4d1. So its valence electrons are in 4d. So we have what? 3 valence electrons. Okay, so we know we're going to be somewhere here. We know we go from krypton, so we start at krypton, and we have 3 electrons to give away. 1, 2, 3. So it puts me at Y for yttrium. This one was gallium. Okay, Y for yttrium. Okay, so that's our next one. You could also say krypton has 36 plus 3 is 39. Element 39 is yttrium. Okay, and our last one is argon, 4s1 3d5. Ooh, that's one of our exceptions because we have a half-filled S and a half-filled D. Okay, so we have to identify those. So since that S does not have a 2, it has a 1, but then we moved on, that means it's an exception. So this is one of our exceptions. So we know it's either going to be chromium or molybdenum or copper and silver. So we're at argon. I have 6 electrons after that, so it's 1, 2, 3, 4, 5, 6. So this is chromium. We could also say that this has 6 valence electrons, and it is in group 6. Okay. So there's many ways to figure it out. However way makes sense to you, do it that way. Okay, let's do some more practice. Without using your periodic table, write the electron configuration of these random elements with the following atomic numbers. So we have 10 electrons, 22 electrons, and 35 electrons. So we can start off using our diagram. 1s has 2. Then we jump up to 2s2. We then go to 2p6, and that uses up all of our elements. And if you cared to look at your periodic table to then see what element this is, this would be neon. Okay, now what I want you to do is pause the video and try these last 2 problems on this slide for 22 electrons and 35 electrons. Okay, 22 electron puts us at 1s2, 2s2, 2p6, that's 10 electrons. So we have 12 to give away. 3s2, 3p6, 4s2, 3d2. So I just followed my diagram until I ran out of electrons. My last one is 35 electrons, so I know I'm going to have the same as at least up to there. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now I have 3d10. Okay, so that leaves me with, that's 30 electrons. I have 5 electrons left, so it's going to go for p5. I'm missing 1 electron, but that's okay. I don't have any more electrons to give away. Okay, so take a second, look those over, double check your own answers against those. If you weren't correct, if you had one wrong or something like that, just make sure you're following this diagram. Okay, and again, it just takes practice. Practice, practice, practice. Okay, and our last practice problem for this lesson is to specify the group on the periodic table in which each of the following elements is found. So we have to look at their valence electrons. Okay, so pull out your own periodic table so that you can look up where these group numbers come from. So we have argon 4s1. So if it's s1, that means there's only 1 valence electron because the core electrons come from argon. So 1 valence electron. This puts us in group 1. Next up we have argon 4s2, 3d10, 4p3. Okay, so if our last electrons come in the p orbitals, this means we're a p block element. So our valence electrons come from the p and the s orbitals because they have the same n value. So we have 5 valence electrons. So this comes from group 5a or group 15. You try the last problem on your own, and I'll write the answer here in a second. Did you get group 8? Or group 8b? Because it is a transition element. Our last electrons are in a d orbital, so this is a d block element or a transition metal. So there's 8 electrons. So group 8 or group 8b. Okay, so that ends our lesson on electron configurations of our elements. Please practice these. Utilize your Alex homework to start practicing these before you move on to our next lesson, where we're going to then be writing electron configurations of ions, which takes the electron configurations of our neutral elements and changes them. So we can't do that until we have a good foundation on this point first. So practice these, master these before you move on.